K Adalarasu, professor in EC department. I am handling the subject for digital image processing, that is today we discuss about the 5th unit of our digital image processing, that is image compression. Before we start about the image compression, we summarizing what are the different units can available for image, what are the different unit already we talked about all the things, that is in first unit about the image processing, we talk about the introduction about the image, what is the definition of the image, what are the properties of the image, that is next one is what are the different transform we can use in the image processing, that is next in second unit we talk about the image enhancement, definition of image enhancement, what is the histogram process, how we can implement in histogram process and image enhancement. Next one is what are the different algorithm can use in the image enhancement technique. Whatever in third unit, we discuss about the image restoration, that is so I have some correlation between the second unit, third unit. What is the second unit? We talk about second unit image enhancement, that is image is already good quality, we can improve, that is so what happened third unit, what is the image restoration? Nothing but the image is already is bad quality, that is we can improve that image quality, that is so what are the different types of filter used in image restoration technique, what are the algorithm we can use, that is so what we will discuss about the fourth unit is image segmentation. Segmentation nothing but the partition, that's meaning English grammatic meaning of segmentation is a partitioning of that. So we can partition image, what are the different algorithm can use partition of the image, that is this is up to this fourth unit, what is now what is the image compression is a different domain in image processing, that is a different domain. So here we need a compression of the image, any image we can do that. Now in this unit we talk about what is the image compression, how image compression is possible to achieve, what are the different techniques that are available for image compression. Now this is the some of the reference book, textbook, all the things we can make it. So image compression, what is about objective of this study, main studies to discuss about the fundamental of the image compression, similarly to study different types of data redundancy, that is so generally we know redundancy nothing but the grammatically we can make the repetition. So most of the information can be repeated, so we can eliminating the repetition, ultimately image compression can be possible to achieve, that is so what is the image compression? So what will happen? Every day enormous amount of information stored, processed and transmit digitally. Method of compression data for prior to the storage, transmission are significant practical and for your commercial interest. Image compression methods are used to what will happen? Reduce the amount of data required to present them. That is what is the main aim of your image compression. Reduce the amount of data required to represent any image. That is a two-way. One is for repeated redundancy, other one is for pictorial information, near relevant information of the image. We can get it. So what is the basic of reduction process, removal of the redundancy data? That is a very crucial play role for image compression, can remove the redundancy. Next, initially analog method in olden days, what will happen? They are using the analog image compression. They reduce the bandwidth of the compression, that is reducing the video transmission bandwidth. Initially they are using the video compression in olden days, analog compression technique they are using. So in 1940, Shannon can introduce the first image compression technique, that is a Shannon entropy technique they are using. So first formulating the probabilistic view of the information and the representation, transmission and the compression. What will happen? Shannon they can make the probabilistic view of the transmission and the compression. Next storage, how we can make it possible to store it. All the things we can make it. Why we need compression? First of all, the main question, why then? To reduce the volume of the data to store, transmit or storing, that is the example facts, that is other one is a text and the images, that is through net you are transmitting many images, that is so what is the second aim? To reduce the bandwidth required for transmitting and to reduce the storage requirement, and that is example speech, audio, video. What is actually this reduce the bandwidth? Most of nowadays video conferencing. Most of the people can foreign professor can make the video conferencing or all the things. So they need some video transmission and that is so similarly reduce the bandwidth. That is most of the nowadays communication one of the crucial play role. How much we can reduce the bandwidth? If reduce the bandwidth, they increase the cost. That is so cost effective. That is most of the Airtel company. They are what is the main aim? They utilize the bandwidth properly. Their reason they are buying the bandwidth through some cost, paying the cost, all the things. That is so these are two aim. One is for storage purpose. Second one is for reduce the bandwidth. This is the main application. We go to the image processing, the image compression. Why need image compression? I give one example. First of all, my present image size is a 512 and a 512. I take the photo for present image. It's a color image. I don't talk about monochrome. Now I take example of color image. That is only differentiate monochrome and color image is a only dimension. Example 512 and 512. It is called as monochrome image. That is only differentiate color image. It's a 512 image dimension into 3. 3 is indicate the primary colors. That is remaining color can be derived from the primary color. So this is identification. This given image is a monochrome image dimension or color image dimension. That is so what will happen? I use a one picture 512 into 3 color image. I can take the space of 786 KB. Same image I can record for 1 second. It will take the space of 23.5 MB. That is if we continue with for 1 minute 1.4 GB. If we still is taking 1 hour, it will take 84 GB. That is so nowadays we could not possible to save the 84 GB. Similarly, the same 84 GB cannot possible to transmit through some of the Wi-Fi network or some of the wireless network we can possible. So in this application we need a compression. That is I give a better example. Why need image compression? Generally, most of the cine movies, if you are taking cine movies, it will take around minimum 20 GB. That is so nowadays most of the theater is satellites telecast. It's not any film room nowadays. That is so suppose you want sending this 20 GB movie, we could not take more bandwidth. So what will happen? They now can use for image compression technique. That is so generally people know what is the initial version of compression is called as a TC rip. That is nothing but theater copy. It's a low compression. Its quality is very bad. Is not it? Next, what is the next level of compression is to make the DVD rip. That is so what will happen is a DVD rip as a improved quality. Next we want another two type of quality. Next one is a Blu-ray. People know the Blu-ray disc. Many people. That is in Blu-ray itself there are two things. Two versions is there. One is if you want the Blu-ray, there is a 720p. And other one is a 1080p. If you go into 720p, what will happen? They have 4.2 GB around. It will take. If you have this 1.0, it will take around 8 GB. So what will happen? Between we don't get much of difference between the 720 and the P9. But image slightly variation. That is not different. That is not. So finally, most of the website they are putting the 1080p. That is automatically they reduce the space. The transmit bandwidth can increase, all the things we can. So that is the purpose only image compression. So generally what is the image compression? Main use of most of the image compression, they are using the multimedia application. That is so most of the multimedia application they are using the image compression. What is the image compression? Nothing but it's a high spatial domain to that is matching up the high spatial domain to low spatial domain. That is matching up your thing. You can make it. So what is the fundamental aim to remove the redundancy present in the data is always which make the image reconstruction possible. Next one is second one, reduce the amount of data required to represent the digital image. That is finally we can use some transformation technique, 2D or 3D transformation or RR transform, ADAMA transform, any mathematical transformation technique we can use that with it. We can make it. So most of the entire this unit, this redundancy can repetition. This word can be automatically repeated redundancy in many places. They can make it. So next, how is a compression is possible? First of all, so first one is a reduce the digital audio, image and video data. We can make it. What is the second one? Properties of human perception. What is the meaning of human? Some of the information cannot be differentiated. Some of the gray levels. Our vision system, some of the gray levels cannot differentiate between one level to other level. So automatically we can eliminate that gray levels. What are the levels are not possible to differentiate? We can eliminate. That is called as your second thing. Properties of human perception. That is so next, digital audio is what is the digital audio? Is nothing but the series of the sample values. Image is nothing but the rectangular array of the pixel value. Image generally represent pixel or gray levels or gray scale. They can make it. So what is the video is nothing but sequence of the image played in a certain manner. That is a frame rate, certain frame rate. That is so they can use a neighboring sample values are correlated. We can check is a correlated or decorrelated. According to this, is a both inference bits are same information or different information we can identify. So what is the data compression? It's a process of reducing amount of data required to represent given quality of information. That is meaning to reduce the number of bits for corresponding image. Main enough is how much possible to reduce the bits for corresponding any image represented. In the quality image also better quality. It's not reduce the quality. We can tolerate the quality of the image also. So what happened? Data redundancy, data that either provided no relevant information or simply restate. What is the redundancy? There is no information, no relevant information or restate. Same information can be restate. We can. One is the best example. That is actually information is data. Any images, what will happen? Most of the information is small part, but the redundancy is a big part. Whatever image compression can eliminate the redundancy, only pick up the information. That automatically our storage space reduces. Your bandwidth also reduces, all the things we can possible touch. This is a graph can be there. So here your redundancy is most of the they can make the most of the redundancy information. Information is small. So final image is nothing but your information with the redundancy. We can make it. One basic example, story. Many people write the story. So story is nothing but some information. Many writers, we can make this information can be transferred into a different way. That is one example. One newspaper magazine, information carrying entire one page. Same another newspaper magazine, only half page. But what is information is only one line. The information can be transmitted to your customer, all the papers in many ways. That is nice. So is one example. What is the redundancy? How it is nice. So what is the example story? Story is information. So where is a data? You are adding all the things are considered as a data. Data redundancy is nothing but if the two individual is different. That is number of words to tell the same basic story. That is a different wording. Somebody take one page write up for convey the information. Somebody only half page is up, they convey the information. That is nice. So at least one include non-essential. What will happen? Some of the non-essential data included in this your magazine. That is nice. So this is said to be contain data redundancy. That is called as a data redundancy. So what is the redundancy? Irrelevant, the unrelevant information or is a reset, same message, reset. That is called as your redundancy. So data redundancy is a central, that is a main issue. Most of the image compression, most of the image processing, the redundancy is the main issue. How would we identify the redundancy? That is one of the crucial area for image compression. That is so using data image compression. Suppose I take the two examples. Suppose having N1 and N2 data, that is denote the number of the information carrying the unit in two data set that are representing same information. Now what will happen in image processing? They are using the two formula. One is so what is the first one? Is RD. RD is nothing but the relative redundancy. D is nothing but the relative. D is a data redundancy. So relative data redundancy. R is a relative. D is a data. Relative data redundancy is nothing but the 1 minus 1 by CR. So where what is the CR is nothing but the is a compression ratio. That is the difference between the two data values. N1 by N2. That is the formula. Now what will happen? I take the two data set N1 and N2. Now what are the three different conditions we can make it? So what will happen? First condition. Suppose N1 equal to N2. So suppose I take N1 equal to both are same data. Number of samples both are same data. That is now. What will happen? CR is 1. Correct? Automatically N1 by N2 CR is 9. So next what is the redundancy? That what is RD? What is the actual use of this RD can be used? How much data can be repeated between the N1 and N2? They check them. That is 9. So next what is the RD is nothing but here 0. Reason 1 by 1 minus 10. That means what is the indicate? There is no repetition between the N1 and N2. Both are same. What is the second case? This is a case 1. In second case what will happen? We can make it N1. N2 is greater than N1. That is meaning denominator is very high. So that is nothing but the CR is infinity. Reason very high. So 1 by that is so we get the infinity. 1 by so 1 by sorry. This is a very infinity. 1 by infinity. Automatically we go to 0. High value N2 is very high. So what will happen? N2 is very high. Automatically CR will come to around approximately how much? That is 9. So 0 point something. Correct? This is example 1 by 100. 0.00. So approximately 0. It will come to 0. So what will happen? RD. RD is nothing but infinity. That is 9. So 1 by 0 infinity, that is 9. So what will happen? Some repetition between the N1 and N2. That is 9. Similarly case 3 now is a reverse. So now N1 is greater than N2 is there. So both the case what will happen? There is some repetition between the N1 and N2. Both are some repetition between them. So here this formula we can use to check the any redundancy between the data set. That is 9. Now we can move on to that one. What previously I taught in Blackboard, that is 9. So your relative data redundancy is a first data set. That is the formula you can use. Compression ratio is nothing but the N1 by N2 all the thing. Here similarly I taught about all the three cases. Whatever first case both the data sets are same. That is N1 and N2 are same. What will happen? Compression ratio. What will happen? RD. So CR is 1, RD is 0. What they infer? What is RD is 0 means what is the infer? That meaning indicate that relative to second data, first representation information contain no redundancy. That is N1 data, N2 data are different. That's no information, same information between the N1 and N2. That's in second case we are taking RD is 1. That's meaning there is a significant redundancy between data. RD is converted. There is some repetition between the N1 and the N2 data that indicate. Whatever case 3, same thing is RD is infinity. That is second data set containing what is the meaning? Second data N2 having much of repetition as compared to N1. N1 less repetition, much of repetition for N2. So this is calculating N1 and N2. Finally, CR varies from 0 to infinity. Similarly, RE varies from 1 to minus infinity. You can make it. That is that. So what is the next? Then I told them mainly where image compressions can possible only two. One is eliminating the redundancy or repetition. Second one is irrelevant psychovisual information. That is that. So in redundancy, we can broadly classify into one is for statistical, other one is a psychovisual. Redundancy can be two classification. One is a statistical redundancy, other one is a psychovisual redundancy. Next model is still classification. That is that. In statistical redundancy is one is a interpixel redundancy, coder redundancy. That is that. So what happened in statistical interval? Say interpixel. That is that. Next one is they make the interpixel and coder redundancy. So interpixel is they are two subdivision. Is a spatial and a temporal. That is that. So generally, first taking top is a redundancy. Two broad classification, one is a statistical and psychovisual. Statistical two classification, one is your spatial and interpixel, that is NAP. So that is coder and interpixel. In interpixel itself we two domain is spatial and temporal, that is NAP. So now move on to the what is the meaning of your starting example coder redundancy, that is NAP. Any image represented in coded form, any image pixel that is can be represented in coded form, that is NAP. Example in Hoffman code, arithmetic code is example of the even coder redundancy. What is the interpixel redundancy? Nothing but that name indicate pixel, interpixel between the one pixel to other pixel. They are apply the concept of neighborhood. That is not. Suppose what will happen? Suppose in the image I take the 2 pixel. This is the image domain. I take the many pixel. This is the image. I have great number of pixel grade level. That is not. Now I take the 2 point A and B. So now I can find out that there is any correlation between the A and B. Generally people know what is the correlation, what is the decorrelation. Correlation nothing but this, some relation is there. What is the meaning of correlation? There is some relation between the two variables, between the example height and weight. That is temperature and rainfall, all the things. That is so there is a relation. What is the decorrelate, uncorrelated? There is no relation. That is so what will happen? Suppose I find out the correlation between the A and B point. They have much correlation, meaning some of the information can be repeated between the A and B pixel. Redundancy is there. That is suppose A and B are decorrelated. Is no correlation, meaning A is a different information, B is a different information. So whatever interpixel redundant, they find out the correlator or decorrelator. How many pixels are correlated, how many pixels are decorrelated. We can calculate. That is the interpixel redundant. Psychovisual redundancy. That name indicates psychovisual. That is a purely is a subjective process. That is generally any techniques are two different type of technique. One is a objective and subjective. That is I give the what is the meaning of subjective and what is the meaning of objective. Suppose I am hitting you. We get the you got the pain, correct? Next what will happen? I ask them, you sense the pain or not? They told them okay, I sense the pain. That is that. So instead of I ask the question, I use some devices. I put some equipment in this body. That is that. Instead of asking, I measure using the devices. Next step. So what will happen? Many of the things, objective process is good. Reason you are using some devices. You are using some instruments. We can quantify the numbers or pain value. That is that. First one is simply ask the feedback. That is that. So why this subjective process very drawback? The reason my perception level is different, your perception level is not. I can quickly identify the pain. Very light pain. Somebody very forcefully hitting only we can sense it. So most of them. So what will happen in psychovisual redundancy? Nothing will purely is a subjective process. We are not done. So what is actually is a vision system. I told them some of the grade levels cannot possible to differentiate the human vision system. That type of grade levels can be eliminated. That is called the psychovisual redundancy. That is a psychological process. That is. So what is the data compression searching? When the one or more this redundancy, that is coder or interpixel or psychovisual, any one or more redundancy can be eliminated, we can achieve the finally in compression. That is that. So this is what are the different things. Example first one is there is a coder redundancy. What is the meaning of coder redundancy? Nothing but the some grade levels are more common than other. That is I take the example in this room. In this room, if we taking falsely, is a white, correct? So it's a common grade levels. Is a most of the common most of white area also common grade. That is one thing. That is called as coder redundancy. What is the second one? If you take the chest, few chests are there. This is a green color. That is not. So that is called the silver interpixel redundancy. That is that meaning the same grade levels cover large area. That is green color covering most of the chests. That is called that is not. Coder redundancy nothing but the some grade levels are more common than other. That is white color is more common from the color or tiles is different color. That is not. So common. That is not. So it considers a coder redundancy, interpixel. What is the psychovisual redundancy? Nothing but the eye cannot only resolve the 32 grade levels. That is now. What will I? What is a crucial play role I? They can only differentiate 32 gray levels. Beyond this, we could not pass to gray levels. That is none. So only in most of the, I told them 720 and 108p, most of them same. That is the reason you are seeing the movie, correct? So actually, you could not possibly differentiate. What is the quality of 720p, Blu-ray, 108p? Is it only slight different? That is none. That is for mainly for PVR. That is cyclovisual redundancy. We can make it. So what is the redundancy type? I told the coder redundancy to reduce the amount of data representing this. So how much data? That is none. How much bits we need for corresponding any images or pixel. That is called as coder redundancy. So interpixel, I told them is a neighboring pixel, is a correlation between the interpixel, all the things. That is interpixel having different type, including spatial redundancy, geometrical, also interframe redundancy. Cyclovisual, I told them the redundancy nothing but the certain information has less relative important for eye vision system. That is none. So in normal visual processing, and we can eliminate it. We can make eliminated system. So now move on to the what is the coder redundancy. So what will happen? Let us assume that this discrete random variable Rk is the interval of taking 0 to 1. They represent the gray levels. That is none. For an image that can each have an Rk occurrence with the probability. That is none. Yeah, an Rk value. That is probability. So what will happen? PR of Rk. What is the PR of Rk is nothing but the. So how we can achieve? What is the code redundancy? How we can possibly achieve the correct? So what is the PR of Rk? Rk is nothing but the Nk by N. What is the Nk is nothing but the number of gray levels occur how many times? Corresponding total gray levels. That is the example. I take the example. This is a gray matrix, image matrix. This is 0, 0, 0, 0, 1, 1, 1, 0, 2, 4, 3, 6. Now, I take 0 gray levels. Take how many? That is nothing but the P0 of R0. Nothing but the 1, 2, 3, 4, 5. That is called as C5. Similarly, gray level 1 occur how many times? Example 1, 2, 3. So 3 times. Gray level 2, how many times? 1 time, 3, 4. That is none. That is considered as Nk. What is the N is nothing? The total number of the pixel called as C. That is none. So we calculate the PR probability of occurring corresponding gray level. That is called as the PR of Rk. That is none. Okay, varies from 0 to L minus 1. What is the L minus 1? Nothing but the your gray level, gray scale. That is none. Example, I use one of the things are any image processing, digital image processing, nothing but the analog to digital converter. Not only digital image processing, signal processing also analog to digital converter play role. That is none. Suppose I take 2-bit ADC. So what is on 2-bit ADC? So now what is the gray levels in the image processing? 2 power 2. 4 gray levels I can get it. 2 power 4. That is nothing but the 0 to 3. 0 indicates the purely black. 3 indicate the pure white. Between this gray levels can be checked. That is called as none. That is none. Now here that is none. L indicate the number of ADC. That is none. 8 means 2 power 8. 256 gray level. That is nothing but 0 to 255 or 1 to 256. That is none. Most of the MATLAB they are not accepting 0. So only we refer the 1 to 256. The ideal case 0 to 255. So what is your L indicate the gray levels. So how many gray levels? What are the gray levels? We can make it all of them. So L number of gray levels. So what is the Nk is the number of times that occur kth gray level. That is the example 0. How many times occur in the image matrix? Great. Similarly 1 occur how many times? All the things. So N is the total number of pixels in the image. We can make it. So now more to the what is the average length bits required to represent the entire information? That is none. So if the number of bits required to represent each value of Rk is L R of t. Suppose none. In the average length of the bit required to represent each pixel, average each pixel or each value, how many average bits are required? Sufficient, we can make. L average nothing but the summation of L R of Rk divided by PR of Rk. PR of Rk is nothing but the probability of occurring corresponding pixel. Example 1, how many times? Probability 1 by n, that is none. Nk by n, that is none. What is the Lk is nothing but the corresponding pixel, probability pixel. What is the code where I mean? That is example 2-bit or 4-bit, anything, that is anything, that can be called as L of Rk, that is none. So finally total number of bit required for coded m into n is a m and L average. That is an example m into n dimension. That is a m is nothing but row, n is nothing but column, is a matrix. Any image is considered as a matrix. What is the difference between signal and image? Signal is a 1 dimension, image is a 2 dimension, is a spatial coordination. So m cross n, that is a row and a column, that is none. Suppose m into n matrix image, what is the average length we require for coded? That is meaning m and L average. We can make it. So what will happen? That is a m and L average. So example, this is a one example, how we can make it. But I can take the 2-way. Say this probability of occurring these gray levels. If we example 1, 2, 3, I can use a 2-way. First way, I can use a standard 3 code, only 3-bit, common for all the things. second case, instead of 3 bit, I can variable word length. That is the example 2 to 2, 3, 4, 6. That is 9. Now, if using these two things, what will happen? L average. That is 9. So, what is the general formula I told them? Summation of the PR of RK into 3. That is 9. So, if we using the standard code at 3, we get the L average is 3. How we can achieve L average? If we adding all the things, we get the 1. So, adding all the things 1 into 3. That is L average. So, what is the second case? For corresponding code word of 2. What is the L average we need? So 0.19 into 2 plus 0.25 into 2 plus all the things summation finally we get. So now this second things, if we have coded form 3, I take in 3 bits common. Entire probability pixel value 3 bits. I can achieve the L average of 3 bit. Second case, if we take in variable code length, I can get only L average 2.7. Automatically I can 0.3 bits I can reduce using the code. That is the code redundancy thing. That is 9. So what is it now? Compression ratio is nothing but 3 by 2.1. That is nothing to 1.111. That is 9. So this approximately 10% of data resulting use of the coded one. That is meaning only 10% having redundancy. So 90% there is no redundancy. That is 9. Automatically we can calculate if 9. So finally to exactly redundancy we can achieve the 9 point. That is 99.9%. That is we can do. So this is another example, same thing, we can make it, find out the coded redundancy, what is the average length, what is the compression, all the things. So if we take two standard, one is a standard code, you could not vary, each gray levels is a 3 bits are set, common, that is not. What is the second case? Coded from 2 variable length, that is the example here, 2 is a 1, is a 2, how many bits considered 2, word length, so word length first one is a 2, 1, 2, 1, all the things. So finally what is the L average? Nothing but the first coded 1 form is a 3, and what is the coded 2 form is nothing but the 0.1 into 2, 0.4 into 1, that is the number of word length is 2, 1, 2, all the things. Finally we can calculate it. Similarly we can calculate the CR value, compression ratio, redundancy, how much redundancy we can make it, all the things here possible. That is not. So next what will happen? So what is an example, another example to find out the your average length code. Similarly, what is the compression related redundancy, all the things. So what happened next? Move on to the coded redundancy, run length code. That is the next one. Variable length coding is assigning a fewer bit to be more probability gray level. That is meaning one previous example, variable length. Instead of all the bits are gray levels, probability levels are instead of 3 given, we can different gray levels or different bits value. That is first gray levels are 2 word code. 3, the other gray levels are 5. We can make it. That is called as your variable length code. All the things. So having coded redundancy, it is almost always present by using the natural binary code. We can make it. So what about interpixel? I told the interpixel redundant nothing but the between the pixel there is any correlation. Neighboring pixel is a decorrelation, all the things. So correlation between the adjacent pixel, that is the value of the neighboring of observed pixel, can be often predicted from the value of the observed pixel. Coding method is having two things we can use in the interpixel. One is for run length code, differential code. We can use a two technique for your code interpixel redundancy. One is for we can make it. So first one we discuss about the run length code. That name indicate run length. That how many times this number corresponding number is running. That is so run length code. Generally run length code can be represent G, L. So G is nothing but the gray levels. N is nothing but how many times the number can be repeated. That is so where the G is a gray levels, L is a number of pixels with the gray levels N, that is length or that is suppose one example 56 figure, this is a gray levels, all the things are here. So now how will you represent in run length code? 56 comma first indicate the gray levels 56 and 56 occur how many times? Example 1, 2, 3, 56 comma, that is one. What is the second one? I take the second gray levels 82. So 82 how many times? So row wise, we go to row wise is a zigzag pattern. If you go to the LCD monitor, all the things are zigzag pattern. That is so what will happen? 82 how many times occur? 83 gray levels how many times occur? That is nothing but the so 56 3, 82 3 times, 83 only 1 times, 80 is nothing but the is a 4 times. That is so total 4 times. That is we can come to this row. So similarly one more time 56 how many occur? All the things 80 how many. So it's a run length code, but nothing but the. What is the main advantage of this type of run length code? Suppose I can transmit this entire information to them. Each having its own bit, they need some bit. Example 56, they need 1 bit. Another 56, another bit. Instead of I can use this type of things, I can make the 53 into 56. That is meaning 3 times 56 happened with 3 times. Correct? Previously, this is only 1 bit sufficient. This 56. Another 3 represent 1 bit. Now only 2 bit. But if you go to this as usual, you can transmit 356, so 3 bit. Now I can reduce 1 bit anymore. So 56 for 1 bit, three times this another bit. So only 2 bit is sufficient for transmit. But as usual, what will happen if transmitting all the thing, they need 3 bits. So only this run length code, main use of this run length code is used for most of the fax machine. That is people show them send the fax. That is so what will happen? Say some of the how many letters are kept, they are shortening. That is another example. Good example. Next slide. What is that? This is another good example. Most of the fax, you are sending the fax nothing but this, some of the word or the text file, correct? So what will happen? Suppose this is a letter, I want to send it the fax, that is now. So what will happen? A, B, B, all the thing. Now, instead of, I can send this letter, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, total 11 bit. Now, instead of I use the run length, how we can represent? A is 2 times, correct? So what will happen? Your A, so 2A. Reason 2 times A can happen, that is fine. B is 3 times, 3. Next I can use hourly run length code for matrix for first row 0. So 0, 8. How many times? 1, 2, 3, 4, 5, 6, 7, 8. So 0, 8. What is the second row? I take 0 is a 2 times, 1 is a 2 times, 2 is a 1 time, 3 is a 3. That is it. 0 it is 2 times, 1 is a 2 times occur, gray levels, 2 is a 1 time occur, 3 is a 3. So similarly we can make it up to 7. If you go to the previous one, if you have to 8, so is gray level, 8 level, 0 occurring 8 times. Is the 8th row, 0. That is the example for how we represent run length code. So main use of your run length code can reduce the number of bits automatically. We can so automatically storage purpose can be reduces, automatically bandwidth also reduces. That is the application we can make. So in data compression, generally we can broadly into classification in any compression. One is a lossy compression and the lossless compression. That name indicate lossless. That meaning during compression your information cannot be lost. That is called as lossless. That is what is a lossy compression? During compression information can be lost, but one important thing is acceptable. Your information loss is acceptable. That is tolerable, anything, anywhere. But that is a very important one. That is your information can be lost, but these losses can be very acceptable. That is so there are 2 types, lossy and lossless compression. Depending upon the application, we can take you need a loss compression, lossless compression. Example, I give the 2 examples. First example, some of the medical imaging. People know the CT, MRI or any MRI imaging. That is in medical field. Similarly, next is movie. Some of the movie. Now, which compression they need a lossy, which compression they need a lossless compression. Suppose in medical field, lossless compression very important. Reason, any small information very important. Is a diagnosis. Suppose you identify any cancer is occur or not in this image. That is not. So, if our information can loss, you are not properly diagnosed. You are misdiagnosed. That is not. So, in this application, most of medical application, what will happen is a lossless compression. During compression, information cannot be lost. That is correct. So, if you see movie, small information, there is a no. It's not a much of effect. You are not dealing with any human system. But in medical field images, you are dealing with human system. Anything go wrong, enter die. So depending upon your application, you select you are taking lossy or lossless compression. Another example, you take the satellite image. Satellite images very few, very important images. What are the satellite they are sending? So all the things are very important. That time don't use a lossless compression. If information can you not predict what is the water content, what is the air content in the all the moon, all the things not possible. Solely that is it. So what will happen? They use a lossy compression, lossless compression for satellite. All video, audio, that is a multimedia application, they are using the lossy compression. And one more very important, if you go to your multimedia, compressing, synchronizing with video and audio. If you are not synchronizing, what will happen? One dialect will go, where moving, screening is different. That is, dialect is different, screen different. You are not mismatched, your dialect and the screen. So compression is very important, crucial field. So it's a lossless and a lossy compression. In lossless method, what are the things they are using? Run length code, Hoffman code, LZW code. In lossy, that is not. So lossy method, most of the video, audio and the text, they are using the lossy compression. They are using the JPEG, MPEG and the MP3. That is not. So generally that G indicate the group. That meaning it's not single people they are producing this one or make the algorithm. Group of people involved to make the algorithm or that is find out the algorithm. That is not. So it's a JPEG, is nothing but the still image. MPEG is a moving image, that is not a dynamic image. Finally MP3 is a audio with a layer of 3. We can make it. So that is all the thing. What are things I thought about what is a lossy and a lossless compression. Lossless compression, there is no information loss and the image can be reconstructed exactly same the original image. That is what is I told them. Suppose you are foreign hospital, you are taking CT MRI image. Suppose Indian hospital, you are taking CT MRI image, but you are not a well doctor in the Indian hospital. The doctor in US, So if you come to that many charger, and we can pay the charger, they are coming on the. So what will happen? What are the CT image you are taking? We are sending to that person. Is lab through net all the thing. That is that doctor analyze and cancer all the thing. That is. Now if you are using the lossless compression, your information can also during reconstruction we get exactly 100% original image. So we doctor can exactly diagnose. That is. Suppose in this case you are using the lossy compression, what will some of the information can lost. Whatever doctor is misdiagnosed. Some of the information lost, they cannot exactly identify what will happen. That is. So that is application. I know the medical imaginary and all the things they are using the lossless compression. What is the lossy compression? Information loss intolerable. That only I told the during definition acceptable and tolerable. If the information loss is acceptable. That is so mainly to one mapping in compression example quantization application commercial system, that is a DVD player, all the things we can make it. Rate concern environmental where the lossless method cannot provide enough compression ratio. Some of them. So most of video audio compression they are using the lossy compression. So medical application, most of they are using the lossless compression they are using. That is. So this is a diagram. What is the image compression and decompression? What will happen is a original image. They are using the compression. They are converting the coded form. What is the meaning? They are not converting image. They are converting some coded form. It's a compressed technique. It's a compact information for storing and transmission any application. What is the during decompression? They get the original image called as exact 100% identity. We get the lossless compression. We don't achieve the compression 100%, only 95% all the thing considered as lossy compression. Information can be lost. That is so that is meaning approximately we can use a original. We can do it. So first we can in lossless compression, that is we can make it augment or augment code and arithmetic code. We can use all the thing. First one is error-free compression. Error-free compression is only acceptable means of data reduction. What will happen? So application is achieved for a medical and a business document. Most of the lossless compression medical application. So where lossless compression usually repeated for legal reason. Processing of satellite image. That only I told. Satellite also very important. Crucial image. That is if you want any image compression, you can apply lossless compression. Error-free. That means error-free. There is no error. Free 100% original image. That is called as. So processing of satellite image that both use and cost of the collecting data make any losses undesirable. So digital radiography, the medical field, radiographic image, whereas loss of information can be compressed, diagnosing, accuracy. That only total. If you are not properly compressed, you are using lossless compression, diagnosing very exactly. If you are not lossy compression, some of the information can be lost, where diagnosing can be missed. That is accuracy can be reduced. That is equally applicable for both binary and gray level images. They are using the both the things. So next, any image compression is a basic model. They are a basic model. What are things? First one is a channel encoder, source encoder, channel encoder, channel decoder, source. It's a look like exactly a communication block. It's a coder, encoder and decoder. Encoder nothing but the many to one, decoder nothing but the one to many. It's exactly communication. What are the digital or any analog communication, digital communication? What are the meaning of encoder, decoder? All the things same meaning. That is not. So this is a general block diagram. So now they are source encoder and a decoder called as a source coded model, codec model. That is not. Another channel encoder decoder is called as the channel codec. That is not. Next, what is very very important for all the model? First, so what is the example of source encoder? So what is the use of this source encoder? Nothing but any image can be converted into binary form, bit form is source. That is the use of source. What is the use of source encoder? Any image is a pixel value. Pixel gray levels can be converted into binary bit form. That is not. So what is the use of this source code? What is one more? They reduce the entropy. If you reduce the entropy, automatically they decrease the average bit required for representing the image. If you coder look like your coder redundancy. In coder redundancy, I can make the flexible coder, correct? One gray level is 3, all the gray levels have 3. Another form, different gray level, different properties are, that is probability value of the pixel values can be represent gray, different value, that is automatically. Same meaning here. So what will happen? Your code is source code, source encoder, what will happen? Converted the image into some binary form or pixel form, that is not. One more use of your source encoder they can use them. Reduce the entropy, automatically they reduce the entropy. If they reduce the entropy, they reduce the number of bit represented or decrease the average bits required for representing the image. That is called that. So what will happen? Next, channel. Channel is nothing but generally communication is a medium. Correct? Channel, general people should know, it's a communication. If you go analog communication, digital communication, if the amplitude modulation, amplitude is your carrier signal, all the things, the frequencies carry all the things. Similarly, yes, a channel is nothing but this is some medium. Whatever actually in image processing channel they represent is a mathematical model. It's a channel look like a mathematical. So what is the use of your channel encoder, decoder, all the thing is a controlled redundancy. They make the controlled redundancy. They can eliminating your noise, communication noises. Example, that is interference noises. That is so what happened, your main use of your channel encoder, decoder, they can use it. They eliminating the communication losses. That is reason you are sending the communication through. Where any image can be sent into some wire, fiber cable, all the that is so the channel encoder can reduce the noises. That is your impulse noise, our interference noise, your all the environmental, all the thing can be eliminated. This one, that is so this your decoder is a reverse of the your encoder. That is so your channel is nothing but some medium. It's a mathematical. We can make it. That is so what is happen? I told you remove the input redundancy. What will happen? Your source they can remove the input redundancy or input how many redundancies are happen. That is increase the noise immunity. That is meaning reduce the noise immunity power. That is I mean. What is immunity? Nothing but I can inject some drug by human body. My immunity power increases. Opposing. That is the same meaning. If the what is this channel encoder, they increase the immunity of the reduce the noise. That is so reduce the noise increase. Your channel encoder input redundancy can be eliminated. That is use of this all the things. So lossless image component, two relatively independent operator. One is for reducing interpixel redundancy, eliminating the coder redundancy. So what will happen? Your lossless image compression. One is for redundancy. That is a reduction interpixel coder redundancy. Both reason your psycho-visual nothing but the subjective point. I call them vision system. We are not talking about here vision system. Only is a objective type. That is so they use for redundancy. That is the interpixel and the coder type. So approach, there are different approach can use them. One is for variable length coding, that is Hoffman code, and the arithmetic code we can use as LZ code. These are the three techniques they are using, the error free or lossless compression. Both are same. We can make it. So variable length code we can use them. That is a reducing coding redundancy. Assign the shortest possible code. That is meaning each bit. This is a maximum possible. This is sufficient. 2 is sufficient. Another bit 6 where length is sufficient. That is meaning. So they can make the shortest possible code where that most probably grade levels. So Hoffman code, arithmetic code is an example for your variable length code. So simple may be either in gray levels of the image or the output of the gray levels mapping operation. We say gray levels of the image or mapping of the system we can make it. That is it. So Hoffman code is the most popular technique for removing your coder redundancy due to Hoffman. It's not a new code. It's generated 1950. It's not a new idea. That is not. Generally, Hoffman code is used in signal processing also. Not only image processing, they are using the signal processing. That is in 1950 they are introducing. That is not. So Hoffman code is the smallest number of code symbol per source symbol. So our source symbol, what is the smallest possible bit need for corresponding? That is for Hoffman code. So resulting code is optimum. We can optimum resultant code. So next Hoffman code, what are the procedures step by step? That is not. So what will happen first step? Yield the smallest possible number of unique code symbol per symbol. That is step 2 step. In what is the step 1? What is that? First one, sort gray levels by decreasing probability. So what will happen? Already each symbol they are given probability. So all the probability first highest to lowest. So highest probability is top, lowest probability is lower. That is not sorting. First is the first step. What is the second step? Add the small nearest possible. That is the small nearest possible we can add it. That is called as the second step. That is not. What is the start step? Next, start the new values of list. What is happen? Next, suppose example 0.1, adding small nearest down, nearest probability. I get the 0.2. Next, start it in the table where the 0.2 is located. Which place is above the 0.3 or anything we can make it. That is not. Next one is repeat until only 2 probability remains. What is the first step? Highest to lowest. Second one is we can add in nearest small probability. Third one is after adding this resultant value where we can locate it in the table. Finally, link the up to 2 probability up to we can add this process. That is what is the step 2? We assign the code. It's a binary. I told you it's a binary code. It's a coded form. It's a so Hoffman code is a coded form. Give code 0 for highest probability. 0 can be given the highest probability. Code 1 given to the lowest probability during adding. That is so go back towards the 3 and add 0 to highest and 1 to lowest one at each node until we can the 2 node. Finally, each symbol or each probability we can identify the how many bits we can make it. That is an example. 0.2. How many word length is sufficient? And one more clearly things. If we are changing 0 and 1, suppose your interest, you are given highest probability is 0, lowest probability 1. There is no issues. Reason here we are not given to code length is very important. It's a code example 0, code length is 2, correct? 1, same code length is 2. But if we are not taking binary conversion here, that is only what is the number of code length, that is not. So 0, 0 also code length true, 1, 0 also code length true. But here very code length true and must. That is instead of code length 3 not. That is we can represent code length 2 is anyway 0, 0, 1, 0, 1, 1 anything. That is so here code length is very important for Huffman code. We can make it. This is example. This is characters. We want to find out the Huffman code of this one. So what is the first step? We can make it this. So first how many symbols occur in this example? Yes, S symbol. Total count how many symbols? 1, 2, 3, 4, 5, 6, 7, 8. Total 8 symbols. So 8. So what will happen? Suppose a symbol S. So P of S by R of S. What will happen? So how many times S occur? 1, 2, 3, 4. So 4 by 8. That is a property. That is it. Similarly, next you go to E. So this is symbol of S. Next symbol E. How many times symbol E occur? Only one times. 1 by 8. Similarly, next N. 2 by 8. Similarly, to all the things we can find out. Next what will happen? We get the 4 by 8 all the things. So we can get the 4 by 8 is around 0.5. Next step. So after we find out the probability, next step is can highest to lowest. That is meaning first symbol come to S, second symbol L 0.25, third one is E is a 0.125, 0.1. After this what will happen? So step 1 is over. That is meaning first ascending order. That is highest to lowest. That is descending order. Second one is second step is adding lowest probability. Now we can add this is the lowest probability. We can actually that is the second step. I can get the result 0.25. Next this 0.25 where I can place. This is the top order. Suppose 0.25 is lower than the 0.5, correct? 0.25, that is right. So here 0.5, both are same. So we can make the same line. Suppose if you are adding both the thing, we get the 0.5. You could not possibly place here. So 0.5 is come to here around. Reason 0.5 is highest to 0.25. So we can make it 0.25. That is right. So we can make arranging even order. That is right. So next 0.25. Next this 0.25 another. What will happen? This is the first row as is it. We can make it 0.5. What is the next row? We adding smallest probability, arranging the which row we can. So 0.25, remaining ditto. We can make it all the things remaining 0.25. That is right. Next what is adding this nearest 0.5. Correct? We can get it. So remaining same 0.5 we transmit. We can rearrange. That is right. So finally stopping. This is right. Next what is the next step? We can assign the code. That is 0 and 1. Suppose what will happen? Both are same value. We can assign the code 0, 1 or 1, 0. Your age, that is right. It is not any fixed rules. Both are unique. We can have 0, 1 or 1, 0. That is right. Next, we can move on to the 0.25. Any 0, 1, 1, 0. That is right. Next, 0.5 into 0.5, we get the probability 1. So don't add 0.5. Leave 2 probability. As is, don't add a last 2 probability. That is right. So commonly we can make it. This is actually a code. Correct? 0, 1, 1, 0, 1, 0, 1, 0. Next, how will it trace out the your corresponding x? How many code length is sufficient? We make the dot line. Correct? So this is example 0.25, 0.25, 0.5, 0 and 1. Suppose I make the 0 and 1 here. So in yes, I can get only 0 code value. Next, N, we can dot the line, trace out the line. So 0, I can get the 1. Correct? Trace out. That is I can make it 1, 0. That is it. Next 0.25, 0, 1, 1. So 1, 1. This line, example dot the line. We can trace out this one. So this is a E. We can trace out this line, we can go to this one, this one. So 1 is a 1 into 0. That is it can make it. W, same this one. If we move on to this one, we are moving. So 1, 1, 1. W. So here I told them, if you making 0, correct. If you making 1 also correct. But very, very crucial to the rule, we can get only one code line. If you get 2, your entire problem is wrong. 0. Similarly, if 1, 0, we get the answer 0, 0, that is no issue. But valid length is 2, compulsory. Here valid length 3 is 3. That is it. Don't change 4, 5. That. But if we represent valid length 3 in any form, 1, 0, 0, 0, 1, any combination we can make it. That is the next one we can make. So after find out all the things, they can make it 3, 4 important things. The other things we can calculate. The first one is a entropy. How much entropy? L average. How much L average bit we need? That is the average number of bits we need. Similarly, entropy value and efficiency. So what is the L average? I told them same formula. That is nothing but the. So L average is nothing but the L average. We can make the summation L R of Rk by P R of Rk. That is nothing but the probability of gray levels. Example 0.5 corresponding value length is 1. So 0.5 plus 1, 0.25 plus into 2. That is nothing else. So 0.5 into 1 plus 0.25 into 2. Plus 0.125 into 3 all the way. That is called as error. That is finally we get the error. This is the first calculation. What is the second calculation? Nothing but the entropy. Entropy is nothing but the is a summation of P R of RK into log of P R of RK. P R of RK is that. If this is a log base 2, suppose I take log base 10, 1 by 0.30 is a log base 10. Suppose I take that is log base 10, we can make it P R of RK, that is. So next finally we can find out the efficiency. This is the third formula for Hoffman code. How will we find out the efficiency? Nothing but the so H of S divided by L average called as the efficiency. So in any Hoffman code, these are the procedure we can calculate. That is finally efficiency how much. So finally they can give the how much efficiency for corresponding Hoffman code. We get the 99% efficiency achieved due to Hoffman code, or 98% we can automatically calculate all the things. So what is the general procedure? First to find out. Suppose they are not given probability value. You calculate the probability depending upon the code. Code value you calculate. Suppose some problem they are directly given the probability value. Suppose corresponding symbol probability directly given, we can assign. Otherwise simple given, you can calculate corresponding symbol what is the probability. That is none. So second step, highest to lowest. That is the second step. What is that? Third step, adding small nearest probability. What is the other step? Assign the code. So what is it? During adding, leave the two probability as is. That is none. So assign them. What is the third one? Make the tree. That is lowest 0 and 1, 0 and 1. Finally find out what is the corresponding grade. That is none. Probability. What is the code length we need. That is none. So using the code length we can. I told them very important. If you have code length 1 is 1, but we can represent the corresponding code length 1. We can any form 0 or 1. Similarly code length 2 we can represent 0 0 1 0 1 1 anything. But must is 2 code length. That is none. So this is I can make it Hoffman code. We can make it. This is another example we can make it on. So they need a 186 general. For using Hoffman code there is only 138. So your bit can be reduced. So if you bit reduce, automatically the storage space reduce, automatically your transmission bandwidth also reduce. That is the one example we can make it. This is another problem. How will you use the Hoffman code? They are directly given grade levels. First problem, they are not directly given. They are not directly given to your probability value, but here they are directly given your probability. So what is the first step? This highest probability 0.25, 0.25, 0.200. So we can assign the symbol. First one is D symbol. That is none. So all the things we can add it nearest probability. We can make it. So A symbol is highest probability, B, C, D. So what will happen? First step, adding small nearest probability, assign the code where, that is the code where 0 or 1 bit, number of bit we can make it. So finally we can make it. So finally next after this, your trace out is very crucial. You are wrongly trace out your corresponding example, 0.5. What is the code word? Is the code word is 1 is 1. That is you are wrongly trace out, your entire problem, L average can be changing mistake, automatically your efficiency also reduced. That is entirely wrong we can. So now 0 0, that means 0 and 0. This trace out this one. If you trace out B, 0 and 1, so 1 0. If you trace out this one, 1 1. If you trace out this one, so 0 1 0. So this is ending point. So whatever ending point, how will you reach the ending point? This is starting point 0. It will go to 1 1. So 0 1 1. So 3. They need 3. Meaning 3 word length is needed. See 3 word. That 3 word length we can make it any represent form 0 0 0 or 1 1 0 1 1 anything. But finally is a 3. Reason you are doing calculation, you are not taking the bits, binary bits 0 0. Only taking code length. How many? Is a 3 or 4 only. That is it. So 0 0. Finally they make the 0. Same starting to ending. We trace out the line. We get it. So this is for your Hoffman code. We can make it. That's the Hoffman table. How many we can make it code length. All the things we can. This is another example problem for making Hoffman code. We can make it. This is how will you trace out the line. We can make it. Next assign the bit. That is we can achieve. That is it. So what is the Hoffman code? Simply taking the binary bits. Isn't it? So one drawback of Hoffman code, if the efficiency is very low. So only you are more on to the arithmetic. What is the next one? If Hoffman code next to is arithmetic code. What is the advantage is a good fast. That is a fast code response is very fastly we can achieve the result. That is not. But one drawback, your efficiency can be reduced. Hoffman code. So you move on to the arithmetic. That is not. So this some of the example we can make it Hoffman code. This is not. So that only disadvantage of Hoffman code. Hoffman use a statistical table. Correct 0 0 1 code length all the things. As a statistical table. All the coding process. So it is rather fast, but does not produce it. That only. It's a fast response, but efficiency is not good. That is not. So these are the Hoffman code. These are some of the disadvantages of Hoffman code. We can make it. So To overcome that is meaning your fast response, your efficiency is good, your response is very fast, your efficiency good. If you go to arithmetic code, but what will happen arithmetic code, here we are not assigning any code, 0 or 1 or 1 0, anything. Simply they can make the interval adjustment, automatically we can make it, that is not. So what will happen, your arithmetic often use a statistical for whole coding, so it is rather fast. What is the next one? It does not produce efficient compression ratio, we can make it. So arithmetic code on the other hand has a different feature, that is it can generate a higher compression ratio. We get a higher compression, but one drawback, response is limitation. Other side limitation also. We get the good compression using the arithmetic code, but efficiency, that is a slow response. We get the compression, that is not. But all the complex calculation take much more time, resulting slower implementation. That is, we get the slower implementation. So sorting of characters with accuracy probability make a message. Suppose what will happen? So what will happen here? Some message is there. To find out the corresponding message, what is a tag? Here, what is the difference between the Hoffman code and arithmetic code? Hoffman code, you find out each probability characters, you find out what is a code, length code, where all the things, correct? But what about in arithmetic code? You could not find out any probability value. That is 0 in the code. You are not assigning 0, 1, 1, 0, anything. That is not. Entire symbol, what is the final tag value? You get only one tag value. This tag value transmitted to you, send it to the transmitter. Receiver end, what is the decoding side? Using the tag, we reconstruct the image or information. Any message we can make it. So according to the corresponding each thing will form separately. So arithmetic code also they are in 3 steps. What will happen? Subdividing of interval 0 to suppose. So what will happen? Entire interval can be subdivided 0 to 1. It's a probability. Reason is a pair of our case probability. So lowest probability is 0, highest probability is 1. So we can sub interval of your probability 0 to 1 based on the probability of source symbol. For each source symbol reference, narrow the interval to the sub interval design. So interval can be sub interval. That is enough. Original 0.2, we can make sub interval still 0.2. That is enough. So subdividing the new interval among the source symbol based on the probability, we can make it. What is finally abandon the end of the message indicator? What will happen? Finally, you find out the only one tag. Finally, abandon end of the message. In receiver end, using the tag, we reconstruct the message. That is it. So encoding is done by choosing any number of intervals for representing data. Is the encoding side. If you go to decoding, is done by retracing the step in coded reconstruction form. This is the one arithmetic code formula. So here order this is simple. I want transmit this message. This message I want transmit. That is it. Now I using arithmetic code. What will happen? Here I don't make it ascending, descending order, anything. Simple. So what will happen? A interval is 0.2. This is a probability corresponding now. So A is again 0 to 0.2 interval. So what is the A2 is nothing but 0.2 to 0.4. That is adding. So 0.4. So what happened next? 0.4 to 0.8. That is next interval of A3. A4 is nothing but finally 1, 0.8. Now, so this is a message I want transmit. That is during a so 0 to 1 maximum probability. So next I divide the interval. So A 0 to 0.2, 0.2 to 0.4, A2 0.2 to 0.8 big interval. A3 is big interval, fine. So now my first values I can transmit. This is A1, A2. This is it. Next what will happen? I can only take this interval. This interval can be magnified. So A1 0 to 0.2. Remaining I can subdivide. So 0.2 can be subdivided for remaining symbols. That is it. Then formula low equal to low plus range of low value, all the thing, high equal to high value, all the thing. So now next what happen? I want to transmit the A2 symbol. Correct A2. Now what will happen? Now this is A2. Correct? Now this sub interval can be magnified. And that is next A3 symbol. This sub interval can be magnified. Within the interval I can assign remaining code. What is each individual A? That is it. Finally this A2 can be magnified. That is it. Now finally this 0.08 only transmit. That is it. Through tag. That is correct. In receiver end, using the 0.06 encoding the process we get. Now I told them compression is good. You are using all the limit. One drawback, you are all the 0.2 correct is a division. All the things small subdivision. It will take much of time. That only other side you are slower. Total things are slower, but the compressions get achieve good result. That is nice. So this is another example. It's a symbol how only arithmetic code we can make it. A code symbol. So 0 to 0.2, another 0.2 to 0.5. That is adding this to 0.5 we get it. Another interval 0.6. All the things. That is similarly same we can make it. Assign the code. What is your code value you want transmit? That is the symbol you want transmit. That is EAII. That is first symbol EA. So first interval E can be magnified. This interval. Next symbol magnified. All the things finally we can achieve one code. See, each interval can be here, this interval can be magnified, next letter is A, we can magnify. So taking only 0.2 to 0.26, in this duration, remaining symbol can be this assigned. That is a subinterval. That is one interval. Interval can be subinterval. That is a procedure. This is a subinterval content. Next I, this interval, that is this can be magnified. Subinterval. 0.26, that is none. So finally we can achieve. So this is a final. 0.2336 is a encoder for same. That is none. Here. That is a different. What is Hoffman code? You are assigning the binary bits, all the things. You are calculating all the things. That is none. So here we are not assigning any bits. We are not taking 1010 anything. Only one final bit. 0.26 is this one can be tagged and send it to the receiver side. Due to using this tag, reason is a 1 bit is sufficient. Suppose I use 1 bit is sufficient. But if we code in Hoffman code, each grade, that is example probability values, they need some value, 3 value, 4 value, all the things. Ultimately they are reducing it. So here arithmetic code is a good compression. That is it. But slow response. Reason is a subinterval. If you go to big images, 0.0004, that is subinterval. That is it. It will calculation take much of time. So only your response is slow. That is the reason why your slow response in arithmetic code. Hoffman code we are not dividing anything. Simply assign the code, adding the two probability 1010 combination. So it's a fast response. Compression is slow, but here arithmetic code your compression is slow, but good. That is it. So very slow response, but good compression we can achieve all the things. So this is another example. We can transmit DAC symbol. We can assign how will you magnify. It's arithmetic code example. So arithmetic code 2 factor limit the code performance in arithmetic. What are the 2 factors? First one is on the end of the message, indicating necessary to separate one message sequence from other to find precise arithmetic. We can exactly precise, nothing but the 2 decimal place, 3 decimal. What is the precise? Nothing but the, you are dividing subinterval, correct? How much decimal you are taking? 2 decimal place or 3 decimal, that is making precise, is not. So that is affecting your arithmetic. How much you are taking? 3 decimal place, after 5 decimal place, automatically they are improving your system. They can make it. So this is the overall difference between the Hoffman code and arithmetic code. So what will happen? Compression method. Compression ratio is very good for arithmetic code. I told the compression efficiency is very bad for that. Next one is the compression speed. Arithmetic code slow. Reason is a subinterval segmentation. So only slow. But whatever here, we are not using Hoffman code subinterval. Simply assign the code is a very fast. That is the reason. Next, decompression speed slow and fast. Memory space similarly very low. Reason they take it. Is Hoffman is slow. What will happen? Very low and low. Arithmetic code taking one. Finally, why arithmetic very low memory space? Only 1 bit, 0.00 tag. You can tag it, only one. But if you go to your Hoffman code, they need binary value 001 or 3 word code, 4 word length, 5 word length. All the things we can make it. So permit random access, no both the things. Compression pattern matching also. Both in arithmetic there is no matching, no. But in Hoffman code, that matching system can be made. That is done. So this is already done for compression method. What are the any compression channel? They need a source encoder, channel decoder, channel. That is a general block diagram of your image compression. We can make it. So source encoder, remove the input reader. That one I showed them. Source encoder is nothing but the converted an image into binary form. Automatically reduce the entropy. Automatically decrease the average bit, our length code. We need corresponding binary form. That is it. Next, each operation designed to reduce eliminating of the 3 redundancy, generally interpixel, coder and psychovisual. Most of your image compression redundancy is repetition. We can make it 3 type only, generally 3 type of redundancy, coder, interpixel and psychovisual we can make it. So they use a mapper, quantization, symbol encoder. In reverse side, they can make the channel, symbol decoder, inverse mapper, we can make it. So mapping your system automatically we can make it. So what is the channel encoder, decoder, all the things we previously discussed how we can make it. So here only one important thing is a quantization. What is it? Most of the image compression. What is a quantization? The process of representing large, that is set of the value with a much smaller set. For example, ADC conversion, one of the quantization. That is most of the your video audio compression they are using quantization. That is most of the MPEG compression. So what is the efficient tool? Most of them take lossy compression. It's not lossless compression. So lossless compression, your Hoffman code, arithmetic code, all the things are lossless compression. That is called as error-free compression. But what will happen? Your lossy compression is example MPEG compression, JPEG compression, all the things are that is any video compression called as lossy compression. That is it. So they are transform, quantization, entropy coding, the channel, entropy decoding, inverse quantization, inverse transform. So what is the general procedure for any your lossy compression? Take the image, make it some transformation. Transformation is already said in first unit. What is the thing? It's a Fourier transform, discrete Fourier transform, Hart transform, Adamar transform, many transformation. 9 transformation. You are using any transformation for your image, converted to other domain. We can find out the your condition after transformation. After condensation, next we can make it the reverse order. This is a reverse transform. Finally, we can. So entire things we can.